Welcome to the discussion. Today we're delving into the paper Estimating Body and Hand Motion in an Ego-Sensed World, which presents EgoAllo, a system for estimating human body pose, height, and hand parameters from egocentric data. The authors tackle a challenging problem: reconstructing a wearer's full body motion from a head-mounted device's limited perspective. What are the key challenges in this egocentric motion estimation problem, and how does EgoAllo address them?
The core challenge is the inherent lack of observability. Egocentric cameras primarily capture the scene in front star of the wearer, leaving most of their body hidden. Accurate estimation requires integrating multiple cues and resolving ambiguities. EgoAllo addresses this by using a conditional diffusion model, leveraging both head pose, proprioceptive input, and image data, visual input for hand estimation. The head pose acts as a strong conditioning signal, guiding the diffusion process towards plausible body configurations.
The paper emphasizes the importance of spatial and temporal invariance in the head motion conditioning. Can you elaborate on why these properties are crucial and how the authors achieve them?
Spatial invariance means the model's predictions shouldn't change if the wearer moves laterally on a flat surface. Temporal invariance means the model's response to a given body motion is consistent regardless of its position within a temporal sequence. These invariances reduce representational redundancy, making the learning task easier and improving generalization. Ego achieves this through a novel conditioning parameterization that locally canonicalizes head motion with respect to the floor plane at each time step. This involves projecting the head pose onto the ground plane and defining a canonical frame relative to this projection.
The choice of conditioning parameterizations significantly impacts accuracy. The paper compares several approaches. What were the key differences, and what were the resulting performance gains?
The paper compares EgoAllo's invariant parameterization against 4 alternatives, using only absolute poses plus local relative pose deltas, absolute poses plus global pose deltas, as in prior work, and sequence-wide canonicalization, as in Ego. The results show a substantial performance improvement for EgoAllo, reducing errors by up to 18% compared to the best-performing baseline sequence canonicalization. This highlights the effectiveness of the proposed invariant representation.
Beyond the conditioning, EgoAllo incorporates visual hand observations during sampling. How does this improve the overall accuracy, and what method is used for hand detection?
Hand observations provide crucial constraints, especially for resolving ambiguities in body pose. The system uses hammer, hands in 3D with the transformers, for hand detection, obtaining 3D hand estimates from egocentric images. These estimates guide the diffusion sampling process, reducing hand estimation errors by over 40% compared to using hammer alone. The integration of hand and body estimation is a key strength of EgoAllo.
The paper mentions a global alignment phase to place the estimated body into the allocentric coordinate frame. Can you explain this process?
After sampling local body parameters from the diffusion model, aligns the estimated body pose with the input slam poses. This is done by computing the absolute pose of the SMPLH root frame using the transformation between the head-mounted device's central pupil frame, CPF, and the root frame of the SMPLH model. This ensures accurate alignment between the estimated body and the scene geometry.
The system also employs guidance losses during sampling. What types of losses are used, and what is their purpose?
Guidance losses are used to incorporate physical priors and visual hand observations into the sampling process. These include a hand observation loss, minimizing the difference between detected and estimated hand parameters, a skating loss, penalizing unrealistic foot movements, and a prior loss, penalizing deviations from the diffusion model's initial predictions. These losses help to refine the estimates and ensure physical plausibility.
How does EgoAllo handle longer sequences than those used during training?
For sequences longer than 128 frames, the maximum length used during training, EgoAllo employs a windowing strategy with overlapping regions. The model processes these windows independently, and then the diffusion paths for overlapping regions are fused using a path fusion technique similar to multi-diffusion. This allows the system to handle arbitrarily long sequences.
The paper evaluates EgoAllo on several datasets. What were the key findings regarding body and hand estimation accuracy?
The evaluation shows significant improvements in body estimation accuracy compared to baselines like Ego, and a variational autoencoder VAE optimization approach. EgoAllo achieves lower MPJPE, per joint position error, and MPJPE, Procrustes aligned MPJPE, scores across multiple datasets. The inclusion of shape estimation is crucial for grounding the estimates in the scene, as evidenced by the improved grounding metric. For hand estimation, EgoAllo significantly reduces errors compared to using Hamer alone, demonstrating the benefits of joint hand-body estimation.
What are some of the limitations of the current EgoAllo system, and what are potential avenues for future work?
The current implementation has some limitations. The test time guidance optimization is computationally expensive, and the performance depends on the quality of the monocular hand estimates from Hamer. Future work could explore more efficient guidance methods, such as training a feed-forward model to replace the optimization step. Improving robustness to hand detection failures is also important. Finally, extending the system to handle more complex scenes with varied terrain would be beneficial.
The paper highlights the importance of spatial and temporal invariance in the design of the conditioning parameters. Could you elaborate on the implications of this finding for other egocentric vision tasks?
The emphasis on invariance is a significant contribution. The principles of designing representations that are robust to irrelevant transformations, like spatial shifts or temporal offsets, are broadly applicable to other egocentric vision tasks. This could lead to more robust and generalizable models for tasks such as activity recognition, scene understanding, and human-robot interaction in egocentric settings. The approach of locally canonicalizing the input data to achieve invariance could be adapted to other modalities and tasks.
The authors use a diffusion model as the core of their system. What are the advantages of using a diffusion model for this particular problem compared to other approaches like recurrent neural networks or graph neural networks?
Diffusion models offer several advantages. Their ability to generate diverse and high-quality samples makes them well-suited for modeling the complex distribution of human motion. The iterative nature of the sampling process allows for easy incorporation of constraints and guidance signals, which is crucial for resolving ambiguities in egocentric data. Furthermore, diffusion models have shown strong performance in various generative tasks, and their architecture is relatively straightforward to implement and train. While RNNs and GNNs could be used, diffusion models offer a more natural way to handle the temporal dependencies and spatial relationships in human motion data.
The paper mentions the use of a mass data set for training. How representative is this data set of real-world egocentric data, and what are the potential implications of using a synthetic data set for training a model intended for real-world applications?
A mass is a high-quality motion capture dataset, but it doesn't directly capture egocentric viewpoints. The authors synthesize egocentric viewpoints and head poses from amassed data. This introduces a domain gap between the training and testing data, which could affect the model's performance on real-world data. Future work should focus on training and evaluating the model on larger, more diverse data sets that include real egocentric data, such as the area digital twins or EgoExo 4D datasets used in the paper's evaluation. The use of domain adaptation techniques could also help to bridge the gap between synthetic and real-world data.
The paper concludes by suggesting several avenues for future research. What do you see as the most promising directions for extending this work?
Improving the efficiency of the test time guidance is a high priority. Developing more robust methods for handling hand detection failures is also crucial. Expanding the training data to include more diverse scenes and more realistic egocentric viewpoints would significantly improve the model's generalization capabilities. Exploring the integration of other sensory modalities, such as inertial measurements from IMUs, could further enhance the accuracy and robustness of the system. Finally, investigating the application of ego allowed to other egocentric vision tasks, such as activity recognition and human-robot interaction, would be a valuable extension of this work.
The paper's findings on the importance of invariance in conditioning parameters are particularly insightful. How might these findings influence the design of future systems for egocentric human motion capture?
The emphasis on invariance should significantly influence future system designs. By prioritizing invariance properties in the design of conditioning parameters and model architectures, researchers can create more robust and generalizable systems that are less sensitive to variations in viewpoint, position, and temporal context. This will lead to more reliable and accurate estimates of human motion in egocentric settings, paving the way for more advanced applications in augmented and virtual reality, robotics, and human behavior analysis.
The use of a diffusion model for generating human motion sequences is a relatively novel approach. How does this compare to traditional methods based on Kalman filters or particle filters?
Traditional methods like Kalman filters and particle filters are often used for tracking and state estimation, but they typically rely on strong assumptions about the underlying dynamics and noise models. Diffusion models offer a more data-driven approach, learning the distribution of human motion directly from data. This allows them to capture more complex and nuanced patterns in human movement, which are difficult to model explicitly. Furthermore, the generative nature of diffusion models allows for the generation of diverse and realistic motion sequences, which is beneficial for applications such as animation and virtual reality.
The paper demonstrates a significant improvement in hand estimation accuracy by integrating body pose estimation. Can you elaborate on the underlying reasons for this improvement?
The improvement stems from the inherent kinematic and temporal constraints imposed by the human body. By jointly estimating body and hand poses, the system can leverage these constraints to resolve ambiguities and reduce errors in hand pose estimation. For example, the position and orientation of the hand are constrained by the position and orientation of the arm and shoulder. The temporal smoothness of hand movements is also constrained by the overall body motion. By incorporating these constraints, the system can produce more accurate and realistic hand pose estimates.
The success of EgoAllo relies heavily on the accuracy of the SLAM system used to provide head pose information. What are the implications of errors or inaccuracies in the SLAM data on the overall performance of the system?
Inaccuracies in the SLAM data will directly propagate to the estimated body and hand poses. Errors in head pose will lead to errors in the conditioning signal, affecting the diffusion model's ability to generate plausible body configurations. The system's robustness to SLAM errors depends on the design of the conditioning parameterization and the ability of the diffusion model to learn from noisy inputs. The use of invariant representations can help to mitigate the impact of some types of SLAM errors, but significant errors could still lead to inaccurate estimates. Future work should investigate methods for improving the robustness of the system to SLAM noise.
The paper mentions the use of a Levenberg-Marquardt optimizer for the guidance losses. Why was this optimizer chosen, and what are its advantages compared to other optimization algorithms?
The Levenberg-Marquardt algorithm is a popular choice for nonlinear least squares problems, which is precisely the type of problem encountered during the guidance phase. It combines the advantages of gradient descent and the Gauss-Newton method. It's robust to ill-conditioned problems and can handle situations where the Hessian matrix is singular or nearly singular. Compared to other algorithms like gradient descent, it typically converges faster and is less sensitive to the choice of step size. Its effectiveness in this context is demonstrated by the significant reduction in hand estimation errors achieved through the guidance process.
The paper focuses on the estimation of human motion in the context of a flat floor. How would the system need to be adapted to handle more complex environments with uneven terrain or obstacles?
Extending EgoAllo to handle complex environments would require significant modifications. The current system relies on the assumption of a flat floor for defining the canonical frame and for applying the skating loss. In more complex environments, a more sophisticated method for estimating the ground plane would be needed. This could involve using techniques from 3D reconstruction or incorporating information from depth sensors. The skating loss would also need to be adapted to account for interactions with obstacles. Furthermore, the diffusion model itself might need to be modified to incorporate information about the environment, allowing it to generate more realistic motions in complex scenarios.
This has been a thorough discussion of the paper. Thank you for your insights.